What if everything you thought you knew about the universe was just the tip of an unimaginable iceberg? Picture this: galaxies racing away from each other at breakneck speeds, not because of some explosive force we can see, but because of something invisible, something mysterious, something scientists call dark energy. This isn't science fiction, it's real, and it's just one of the countless unseen forces pulling the strings behind the curtain of reality. From the ghostly tug of gravity bending light around galaxies to the cosmic web of dark matter weaving the very structure of existence, our universe is a stage where the most powerful actors remain hidden in the shadows. Think about the last time you felt the wind on your face. You couldn't see it, but you knew it was there, just like these invisible forces shaping the cosmos. They don't glow, they don't cast shadows, and yet they hold entire galaxies together, warp the fabric of space-time, and dictate the fate of everything we know. Some ripple through the universe like gravitational waves, echoing collisions of black holes that happened billions of years ago. Others lurk in the void between stars, pushing and pulling with a power we're only beginning to understand. These aren't just quirks of physics, they're the architects of reality itself. So what are these hidden forces, and how do they shape the universe in ways we can't even see? Buckle up, because we're about to embark on a journey through 30 of the most mind-bending, awe-inspiring phenomena that defy our senses and challenge our understanding of everything. From the quantum realm's bizarre behavior to the vast, mysterious energies stretching the cosmos itself, we'll uncover the unseen hand sculpting existence. This isn't just a tour of the universe's greatest mysteries. It's a front-row seat to the forces that make you, me, and everything we've ever known possible. Ready to pull back the curtain? Let's dive in. Let's start with the most baffling force of all: dark energy. Imagine the universe as a balloon, inflating faster and faster with every passing second, not because of anything inside it, but because of some invisible hand stretching it from the outside. That's essentially what dark energy does. In 1998, astronomers made a shocking discovery while observing distant supernova. The universe wasn't just expanding, it was speeding up. This wasn't just unexpected, it defied everything we thought we knew about gravity. If the cosmos were a car, dark energy would be the accelerator pedal stuck to the floor, and we have no idea who or what is pressing it. Here's the paradox: dark energy makes up about 70% of the universe's total energy budget, dwarfing everything else: stars, planets, even dark matter. Yet we can't see it, touch it, or detect it directly. It doesn't interact with light or matter. It simply warps space itself, driving galaxies apart at ever-increasing speeds. Think of it like an anti-gravity force woven into the fabric of reality, a cosmic repulsion stronger than gravity's pull. Scientists are racing to unravel this mystery. Missions like the Euclid Space Telescope are mapping the universe in unprecedented detail, searching for clues in the way galaxies cluster and light bends. Some theories suggest dark energy could be linked to the vacuum of space itself, a kind of background energy that grows stronger as the universe expands. Others propose it's evidence of an entirely new physics, one we haven't even imagined yet. One thing's certain: whatever dark energy is, it holds the keys to the universe's ultimate fate. Will it tear everything apart, or could it suddenly vanish, leaving gravity to pull everything back together? For now, it remains one of the greatest puzzles in all of science. Now imagine trying to hold a galaxy together with nothing but gravity from the stars and gas we can see. It would be like building a skyscraper out of tissue paper. The math just doesn't add up. Stars on the outer edges of spiral galaxies rotate so fast they should fling themselves into the void, yet they don't. Something invisible is gripping them, an unseen scaffold of gravity holding everything in place. That something is dark matter, the universe's hidden skeleton, outweighing ordinary matter 5-1. Here's the eerie part: dark matter doesn't just lurk passively. It sculpts the cosmos. Picture a spider's web, invisible until dew collects along its strands. Similarly, dark matter's gravitational pull draws regular matter into vast filaments, creating a cosmic web where galaxies cluster like beads on a string. Without it, the universe would be a scattered, formless void. Yet it refuses to interact with light, leaving us with only ghostly traces, the way it bends starlight around galaxies like a lens, or the way it tugs at entire clusters of stars, making them move in ways Newton's laws can't explain. Scientists are hunting this phantom with experiments like LUX Zeppelin, a detector buried a mile underground to shield it from cosmic noise. It's searching for WIMP, weakly interacting massive particles, hypothetical dark matter candidates that might occasionally bump into ordinary atoms. Other projects like the Vera Rubin Observatory are mapping distortions in starlight to trace dark matter's fingerprints across the sky. The stakes couldn't be higher. If dark matter is real and the evidence is overwhelming, it means we're surrounded by an invisible ocean of particles, a shadow universe that shaped our very existence. Yet after decades of searching, we still don't know what it's made of. Is it undiscovered particles, primordial black holes, or something even stranger, rewriting the rules of physics itself? One thing's certain: until we solve this riddle, we're like ants trying to understand the wind by watching leaves tremble, aware of the force, but blind to its true nature. Even empty space isn't truly empty. If you could peer into the void between stars with a microscope powerful enough, you'd witness a frenzy of activity particles and antiparticles flickering into existence for mere fractions of a second before vanishing again. This isn't science fiction, it's quantum vacuum fluctuations, one of the strangest and most fundamental forces shaping reality at the smallest scales. Imagine the fabric of space as a turbulent ocean, with waves constantly rising and falling. Only here, the waves are particles, and their brief lives are governed by the uncertainty principle, which allows them to borrow energy from nothingness just long enough to leave a mark on the universe. These fleeting particles aren't just theoretical curiosities, they have real, measurable effects. Take the Casimir effect, where two uncharged metal plates placed incredibly close together in a vacuum will inexplicably be pushed toward each other. Why? Because the space outside the plates allows for more of these quantum fluctuations than the narrow gap between them, creating a kind of pressure differential that nudges the plates together. It's as if the universe itself is restless, its hidden energy constantly pushing and prodding at the boundaries of what we consider possible. Then there's zero-point energy, the idea that even at absolute zero, the temperature where all classical motion stops, space still thrums with residual energy. This isn't just a tiny background hum. Some calculations suggest the vacuum of space could contain unimaginable amounts of it. If we could tap into even a fraction, it might revolutionize energy production or, as some speculate, even enable warp drives by bending space-time itself. But there's a catch. This energy is locked away in the quantum realm, flitting in and out of existence too quickly for us to harness. The implications stretch beyond the lab. Some theories suggest quantum fluctuations in the early universe may have seeded the first galaxies, tiny ripples magnified by cosmic inflation into the vast structures we see today. Others wonder if dark energy itself could be tied to the vacuum's hidden activity, a kind of cosmic repulsion born from nothingness. Whatever the truth, one thing's clear: what we call empty space is anything but. It's a simmering cauldron of potential, a reminder that the universe's most profound mysteries often lie not in the stars, but in the seemingly silent spaces between them. One moment, the entire observable universe was smaller than a single atom. Then, in less than a trillionth of a second, it exploded outward faster than the speed of light. This wasn't the Big Bang itself, it was something even more mind-bending. Scientists call it cosmic inflation, a runaway expansion that stretched space so violently, it ironed out wrinkles in the infant cosmos and set the stage for everything to come. Without it, the universe as we know it wouldn't exist. Here's why inflation matters. Picture two patches of sky on opposite sides of the universe. They're so far apart, light hasn't had time to travel between them since the beginning of time, yet they're nearly identical in temperature. How it's like walking into a bakery and finding two cupcakes baked in separate ovens, each at exactly 425 degrees down to the decimal. That shouldn't happen unless something synchronized them. Inflation solves this horizon problem by proposing those regions were once neighbors, stretched apart faster than light could keep up. Then there's the flatness problem. The universe's geometry is suspiciously balanced like a pencil perfectly upright on its tip. Too much matter and space would curve inward in a big crunch. Too little and it would fly apart into nothingness. Yet after 14 billion years, measurements show space is flat to 1 part in 10,000. Inflation explains this by stretching the cosmos so thin, any initial curvature became negligible, like blowing up a balloon until its surface feels smooth to an ant. But how do we prove it happened? Teams like Bicep and Keck are hunting for primordial gravitational waves, ripples in space-time from inflation's violent expansion. These would leave faint swirls in the cosmic microwave background, the afterglow of the Big Bang. In 2014, Bicep too thought they'd found them, only to realize cosmic dust muddied the signal. The search continues with ever more sensitive detectors. Some theories suggest inflation wasn't a one-time event, but part of an eternal cycle. Pocket universes bubbling up endlessly in a multiverse. Others propose alternatives, like a bouncing universe collapsing and rebounding without inflation. But the evidence tilts strongly toward that explosive stretch, a moment when the laws of physics as we know them were rewritten. If confirmed, it would mean our entire cosmos is just one smoothed-out corner of something far grander, a single note in an infinite symphony of universes. Black holes were supposed to be cosmic one-way streets. Anything that crossed their event horizons vanished forever, erased from the universe. That's what we believed for decades until Stephen Hawking dropped a bombshell in 1974. He proposed that black holes aren't completely black, they glow, not with light as we know it, but with a faint whisper of radiation now called Hawking radiation, slowly bleeding away their mass over eons. This revelation was staggering, but it came with a terrifying implication. If a black hole eventually evaporates, disappearing into nothingness, what happens to all the information it swallowed? Stars, planets, even entire civilizations, are they truly gone forever? This isn't just about lost data. In quantum mechanics, information can't be destroyed. It might get scrambled, but it's always recoverable in principle. That's why your burned toast still carries traces of what it once was. But black holes seem to break this rule, swallowing information without a trace. The conflict between Hawking's math and quantum theory became known as the black hole information paradox, and it's been tearing physics apart ever since. Enter the firewall theory, a radical idea suggesting the event horizon isn't the serene boundary we imagined. Instead, it might be a raging wall of high-energy particles incinerating anything that approaches. Think of it like walking into what you thought was a quiet forest, only to find it's actually the mouth of a blast furnace. This solves the information problem by ensuring nothing ever truly enters the black hole intact, preserving quantum laws. But it comes at a cost, rewriting Einstein's vision of smooth space-time near the horizon. Then there's the holographic principle, which proposes something even stranger. The information inside a black hole might not be lost at all. It could be encoded on its two-dimensional surface, like a cosmic DVD. Just as a hologram stores a three-dimensional image on a flat sheet, a black hole's interior might be a projection of data painted on its event horizon. If true, it would mean our entire three-dimensional universe could be a holographic illusion, with reality unfolding on some distant, invisible boundary. Experiments like the holometer at Fermilab are searching for evidence of this pixelated reality. while theorists wrestle with equations that bridge quantum mechanics and gravity. Some argue information leaks back out via Hawking radiation, scrambled beyond recognition but technically preserved. Others suggest black holes might spawn baby universes carrying the information elsewhere. One thing's certain, solving this paradox could reveal deeper layers of reality itself, proving once again that the universe's greatest mysteries don't lurk in distant galaxies. They're hidden in plain sight, written in the fabric of space and time. Imagine a particle so elusive it could pass through a light year of lead without a single collision. That's the neutrino, nature's ultimate ghost, streaming through you right now by the trillions, utterly unnoticed. For decades, we thought these phantoms were massless, zipping through the cosmos at light speed without a whisper of interaction. Then came the bombshell discovery. Neutrinos aren't just passing through matter, they're shape-shifting as they go. This phenomenon, called neutrino oscillations, upended physics. Picture a chameleon mid-stride, shifting from red to blue to green before your eyes. Similarly, neutrinos exist in three flavors: electron, muon, and tau, and they spontaneously morph between them mid-flight. The catch: quantum mechanics says such transformations are only possible if neutrinos have mass, however tiny. That revelation punched a hole in the standard model, our most precise theory of particle physics, which had assumed neutrinos were weightless. Suddenly, we faced a universe where even the most ephemeral particles carried secrets heavy enough to rewrite the rules. Detecting these phantoms requires feats of engineering bordering on madness. Take IceCube, a detector buried deep in Antarctic ice, turning a cubic kilometer of glacier into a neutrino telescope. When a rare collision occurs, it creates a flash of blue light, Cherenkov radiation captured by thousands of embedded sensors. Some of these neutrinos hail from beyond our galaxy, having traveled billions of years untouched before striking the ice. In 2018, IceCube traced one back to a blazar, a supermassive black hole spewing jets of particles, proving these ghosts can carry cosmic messages across unimaginable distances. But why does this matter? Because neutrinos might hold clues to why the universe favors matter over antimatter. During the Big Bang, equal amounts should have annihilated each other, leaving nothing behind. Yet here we are. Neutrinos, with their subtle asymmetries, could explain this cosmic imbalance. Future experiments like Dune will shoot neutrino beams through 800 miles of Earth to study these oscillations in unprecedented detail. The deeper we dig, the stranger it gets. Some theories suggest neutrinos could be Majorana particles, their own antimatter twins. Others speculate they might interact with dark matter. Whatever the truth, these shadowy particles remind us that even the most silent observers in the cosmos can scream revelations if we're willing to listen. Magnets are everywhere, holding notes to your fridge, guiding compass needles, even buried in your phone's speakers. But here's the catch: every magnet we've ever found has two poles, a north and a south. Break one in half and you don't get isolated poles, you just create two smaller dipoles. This symmetry is so fundamental, it's baked into Maxwell's equations, the very foundation of electromagnetism. But what if nature isn't so symmetrical after all? Enter magnetic monopoles, theoretical particles carrying just a single magnetic charge, either north or south, with no opposite counterpart. Their existence would upend centuries of physics. The idea traces back to Paul Dirac in 1931, who showed something extraordinary. If even one magnetic monopole exists somewhere in the universe, it would explain why electric charge comes in discrete, quantized units. Think of it like a cosmic barcode. Dirac's math revealed that the product of an electric charge and a magnetic charge must be a whole number multiple of a fundamental constant. Suddenly, the fuzzy spectrum of possible charges snapped into sharp focus, with monopoles acting as nature's accounting system. But the implications go deeper. Grand unified theories, ambitious frameworks aiming to merge electromagnetism with the strong and weak nuclear forces. predict these solitary magnetic charges should have formed in the searing heat of the early universe. When the cosmos was 1,000,000,000,000 degrees hot and all forces were indistinguishable, cracks in the fabric of reality might have frozen into existence as monopoles, relics of a more symmetrical age. Some theories suggest they'd be unimaginably dense, packing the mass of an entire bacterium into a space smaller than a proton. So why haven't we found one? The hunt has spanned decades, from tunneling through ancient mica crystals for trapped monopoles to scanning moon rocks with superconducting detectors. Even the Large Hadron Collider has kept an eye out. The challenge, if they exist, they're staggeringly rare, perhaps diluted to one per galaxy by cosmic inflation. Or they might be hiding in plain sight, masquerading as cosmic rays or lurking in magnetic fields we can't yet map. The stakes: a monopole discovery wouldn't just rewrite textbooks, it could revolutionize technology. Imagine circuits powered by magnetic currents or quantum computers leveraging monopole quirks. More profoundly, it'd prove that the universe's forces were once united, a glimpse into nature's deepest symmetries. Until then, these phantom particles remain both a tantalizing possibility and a ghostly reminder of how much we've yet to uncover. There's a whisper in the cosmos so faint, it takes a cathedral of magnets and a symphony of superconducting technology just to hear it. These whispers could come from axions, ghostly particles so light, a single gram could hold more of them than there are stars in the observable universe. Theorized in the 1970s to solve a quantum puzzle you've never heard of, axions have since emerged as leading suspects in the hunt for dark matter. Unlike their bulky WIMP cousins, axions wouldn't crash into detectors, they'd dance through them, leaving only the subtlest of footprints. Imagine a universe where dark matter isn't some exotic heavy particle, but a cosmic fog of ultra-lightweight axions, collectively outweighing all visible matter 5-to-1. Their existence would solve two mysteries at once: the dark matter enigma and the strong CP problem. A head-scratcher about why quantum forces respect certain symmetries in ways they shouldn't. It's like discovering a single key that opens two seemingly unrelated locks, one governing the balance of the cosmos, the other hidden deep in the nucleus of every atom. To catch these phantoms, scientists built the Axion Dark Matter Experiment, ADMX, a high-tech ear pressed against the universe's quietest frequency. Picture a massive superconducting magnet, chilled to near absolute zero, with a cavity inside so sensitive it can detect individual photons born from axion conversions. Here's how it works. Under intense magnetic fields, axions should occasionally transform into microwave photons, like shadows briefly flickering into light. ADMX tunes its cavity like a cosmic radio, scanning one frequency at a time, listening for that telltale hum. The challenge: axion signals would be billions of times weaker than background noise. It's like trying to hear a single note played by a violin in another galaxy while standing in the middle of a hurricane. To overcome this, ADMX employs quantum amplifiers so precise they operate at the edge of Heisenberg's uncertainty principle, a technological marvel that would have been science fiction just decades ago. Why go to such extremes? Because if axions are real, they might be everywhere, flowing through you right now as a cold, invisible wind. Some theories suggest they could even form Bose-Einstein condensates, quantum superstructures stretching across galaxies. Others propose they interact so weakly that detecting them requires reimagining physics itself. Whether ADMX finds them or not, the pursuit reveals something profound. In the hunt for the universe's hidden architects, sometimes the quietest voices hold the loudest truths. Gravity keeps your feet on the ground, electromagnetism powers your devices, and two nuclear forces hold atoms together. These four fundamental forces have explained everything from falling apples to shining stars for over a century. But what if there's a fifth player lurking in the shadows? Recent experiments with muons, unstable cousins of electrons, have sent shockwaves through physics, revealing anomalies that just might betray the existence of a secret force rewriting nature's rulebook. Picture a spinning top wobbling slightly off-axis, defying expectations. That's essentially what's happening with muons in powerful magnetic fields at Fermilab's G-2 experiment. According to quantum theory, these particles should dance with predictable precision as they interact with virtual particles popping in and out of existence. Instead, their wobble, measured with precision down to parts per billion, drifts slightly off course, as if nudged by something invisible. The discrepancy is tiny, but in particle physics, even whispers can herald revolutions. This anomaly might trace back to an unknown force carrier, a hypothetical particle mediating interactions we've never witnessed. Unlike gravity or electromagnetism, this fifth force would be feeble and long-range, perhaps only noticeable at subatomic scales or cosmic distances. Some theories suggest it could be linked to dark matter or hidden dimensions, acting as a bridge between our visible world and the universe's shadowy layers. Imagine trying to communicate with someone through a thick wall. You might not see them, but if they occasionally tap in a pattern, you'd know they're there. The muon's wobble could be that tap, a coded message from physics beyond our current understanding. Skeptics argue these results might stem from unaccounted for errors or gaps in existing models. After all, quantum calculations are fiendishly complex, and the standard model has withstood every test for 50 years. But the G-2 data aligns with earlier hints from Brookhaven National Lab, and when independent experiments start echoing each other, physicists take notice. Upgraded detectors at Fermilab are now pushing precision further, while theorists scramble to map out what a fifth force might look like, whether it's transmitted by a fleeting Z-prime, boson, or tied to symmetries we've yet to uncover. The implications are staggering. A new force could explain cosmic mysteries like dark energy's push or dark matter's pull. It might reveal connections between seemingly unrelated phenomena, much like Maxwell unified electricity and magnetism centuries ago. Or it could expose flaws in our most cherished theories, forcing a rewrite of reality's blueprint. For now, the muon's whisper remains tantalizingly ambiguous, a riddle wrapped in a quantum enigma, waiting for the next experiment to shout its secrets. Right now, beneath your feet and in the air you breathe, there's an invisible scaffold holding reality together, the Higgs field. It's what gives particles their mass, what makes the universe stable, what lets stars burn and planets form. But what if this field isn't as stable as we think? What if it's teetering on the edge of a cosmic cliff, waiting for the slightest nudge to send it crashing into a new state, one where the laws of physics as we know them cease to exist? This isn't just hypothetical, it's called vacuum decay, and it's one of the most unsettling possibilities in all of physics. Imagine the universe as a valley, with the Higgs field sitting in a shallow depression, a false vacuum. It's stable for now, but there might be a deeper valley somewhere, a true vacuum with entirely different rules. If a tiny patch of space somewhere in the cosmos quantum tunnels into that lower state, it could trigger a bubble of true vacuum expanding at the speed of light. Inside that bubble, the Higgs field would reconfigure itself, rewriting the very fabric of reality. Atoms might not hold together, forces could behave differently. Everything we know, galaxies, planets, life itself, would unravel in an instant. The terrifying part, we wouldn't see it coming. A bubble could already be expanding toward us from some distant corner of the universe, and by the time it reached Earth, our last moment would be a silent, instantaneous rewrite of existence. No explosion, no warning, just physics itself turning inside out. This isn't science fiction. Calculations based on the Higgs boson's mass suggest our vacuum might indeed be metastable, stable enough to last billions of years, but not forever. Experiments at CERN are probing this very question, measuring the Higgs properties with unprecedented precision to determine whether we're sitting on a time bomb or a solid foundation. Some theories even suggest that high-energy particle collisions could, in principle, create a tiny bubble of true vacuum. though the odds are so astronomically low, it's far less likely than winning every lottery in history simultaneously. Yet the implications are profound. If vacuum decay is possible, it paints a picture of a universe where the ground beneath our feet is fundamentally fragile, where the constants we depend on might just be temporary. It's a humbling reminder that the forces shaping our reality are not just invisible, they're unpredictable. And in the grand scheme of things, we're just borrowing time in a cosmos that could rewrite itself at any moment. What if gravity isn't a fundamental force at all, but something far more surprising? A side effect of chaos itself. That's the radical idea behind entropic gravity, a theory that flips centuries of physics on its head by suggesting gravity emerges from the universe's inherent disorder, like a cosmic mirage rising from the depths of entropy. At the heart of this idea lies a simple but profound question. Why does gravity behave exactly like a force when it might not actually be one? Picture a crowded room where everyone's jostling for space. The movement isn't directed by any invisible hand. It's just the natural outcome of people trying to maximize their freedom to move. Now imagine the universe as that room, with entropy, the tendency toward disorder, acting as the driving force behind what we perceive as gravity. According to physicist Eric Verland, massive objects like stars and planets don't curve space-time because of some fundamental force. They simply reshape the way information is distributed in the cosmos, creating gradients of entropy that look like gravity to us. It's as if we've spent centuries studying shadows on a wall, mistaking them for the objects casting them. The implications are staggering. If gravity is emergent rather than fundamental, it could explain galactic rotation curves without invoking dark matter. Take spiral galaxies, where stars orbit so fast they should fling into space, yet they don't. Dark matter theorists say invisible halos hold them in place. But entropic gravity suggests another answer. The information content of space itself changes near massive objects, altering the rules of motion in ways that mimic extra mass. It's like realizing the floor you thought was tilted is actually flat, and your sense of balance was tricking you all along. Critics argue Verland's math doesn't yet match observations as precisely as dark matter models. But supporters point to oddball galaxies like NGC 1052, where stars move wrongly even for dark matter, yet fit entropic gravity's predictions. The debate rages with experiments like the Laser Interferometer Gravitational Wave Observatory scrutinizing gravity's behavior in extreme environments. Could ripples in space-time reveal hidden layers of entropy, or will dark matter's decades of predictive success prove too robust to overturn? Either way, entropic gravity forces us to confront a humbling possibility. The universe's most familiar force might be a grand illusion, a byproduct of deeper, more subtle laws we're only beginning to glimpse. And that's the beauty of physics sometimes. The answers aren't hidden in the equations, but in the spaces between them. Time crystals sound like something ripped straight from the pages of a sci-fi novel, structures that pulse and oscillate forever, not because they're powered by some external force, but because they exist in a bizarre new phase of matter where time itself becomes part of their architecture. These aren't just theoretical curiosities. In 2017, scientists at the University of Maryland and Harvard brought them to life in labs, chilling atoms to near absolute zero and coaxing them into a dance that defies one of physics' most sacred laws, the arrow of time. At first glance, time crystals seem to break the rules. Imagine a pendulum that swings back and forth indefinitely without any push or energy input. That's impossible, right? Yet in the quantum realm, time crystals achieve something eerily similar. They're not perpetual motion machines. They don't violate thermodynamics because they don't do work. Instead, they exist in a ground state, the lowest possible energy configuration, yet their atomic structure oscillates with clockwork precision. It's as if you froze a river solid and still saw the water molecules ripple in perfect, unchanging waves. How does this work? The secret lies in a phenomenon called time translation symmetry breaking. Normally, the laws of physics look the same no matter when you observe them, a principle that's held since Newton. But time crystals shatter this symmetry, locking into a rhythm that repeats at fixed intervals like a cosmic metronome. In the Maryland experiment, researchers used a chain of ytterbium ions, entangled their quantum states, and then pulsed them with lasers. Instead of responding in sync with the laser's rhythm, the ions fell into their own slower beat, a signature of time crystalline order. What's truly mind-bending is what this implies about the nature of time. Could the universe itself harbor hidden time crystals, structures that have been ticking away since the Big Bang? Some theorists speculate they might exist in exotic materials or even in the quantum vacuum, their oscillations so subtle we've yet to detect them. Others see potential for quantum computers where time crystals could act as flawless, self-correcting memory units, preserving information against the ravages of decoherence. Yet the most profound revelation might be philosophical. Time crystals force us to confront the idea that time isn't just a backdrop for events. It can be woven into matter's very fabric, a dimension as tangible as length or width. They hint at a universe where the distinction between space and time blurs, where the ticking of a clock isn't just a measurement but a property of reality itself. And that's the beauty of physics sometimes. The most impossible-seeming ideas turn out to be hiding in plain sight, waiting for us to look at the world sideways. Here's something that would make even Einstein raise an eyebrow: two particles separated by the width of a galaxy, instantly influencing each other's properties as if connected by an invisible thread. This isn't science fiction, it's quantum entanglement, a phenomenon so bizarre Einstein himself called it spooky action at a distance. But what if this eerie connection isn't just a quirk of tiny particles? What if it's the glue holding space-time itself together, especially in the chaos of black holes? Picture two entangled particles, let's call them Alice and Bob, spinning in perfect sync. Measure Alice's spin as up, and Bob's instantly becomes down, no matter how far apart they are. This happens faster than light, seemingly violating relativity's cosmic speed limit. But here's the twist: no information is actually transmitted. It's like having two coins that always land opposite sides when flipped, no matter where they are in the universe. The correlation is baked into their shared quantum state from the moment they're created. Now zoom out to black holes, where entanglement takes on a cosmic role. The AR equals EPR conjecture, a brainchild of physicists Leonard Susskind and Juan Maldacena, proposes something revolutionary. Entangled particles might be connected by microscopic wormholes or Einstein-Rosen bridges. In this wild vision, what we call entanglement isn't just a statistical link. It's a physical tunnel through space-time itself. A black hole's interior could be secretly wired to the radiation it emits outside, with entanglement acting as the invisible stitching holding the fabric of reality together. This idea isn't just theory. Quantum satellites like China's Missus have tested entanglement across record-breaking distances, beaming photons to ground stations over 1,200 kilometers apart. The particles stayed eerily in sync, proving quantum weirdness persists even in Earth's orbit. Future missions aim to push these tests to interplanetary scales, probing whether entanglement truly withstands the vastness of space. Yet the implications go deeper. If ER equals EPR is right, black holes might not be the information-destroying monsters we once feared. Instead, their interiors could be encoded in the Hawking radiation they emit, with entanglement serving as the cosmic backup drive. Imagine a scrambled hard drive that, when viewed through the right lens, reveals its data perfectly preserved in the static. That's the promise of this radical idea, one that could reconcile quantum mechanics with gravity at last. So the next time you hear spooky action, remember, it might not be spooky at all. It could be the universe's most elegant wiring, a hidden architecture turning the chaos of black holes into the ultimate quantum puzzle box. And we're just beginning to crack the code. Picture the universe in its infancy, a seething cauldron of energy and forces so extreme they could twist the very fabric of reality into knots. Among the relics that might have survived from that chaotic era are cosmic strings, hypothetical cracks in space-time, thinner than a proton yet stretching across entire galaxies. Imagine a scar left behind after the universe healed from its earliest wounds, a flaw in the cosmic tapestry so dense, just one of these strings could outweigh Mount Everest, yet so narrow you could pass right through it without noticing. These aren't ordinary strings, they're space-time defects thought to have formed during the universe's first fractions of a second as fundamental forces split apart. Picture a lake freezing over. Ice crystals form in patches, and where those patches meet, cracks appear. Cosmic strings are like those cracks, but in the geometry of reality itself. Unlike black holes, they don't curve space into a pit, they wrinkle it, creating long, invisible threads of concentrated energy. If one sliced through Earth, the only clue would be a fleeting distortion in the paths of passing stars as their light bent around its immense gravitational field. The real magic happens when these strings move. As they oscillate or snap, they could send out gravitational waves, ripples in space-time so powerful they dwarf the signals from colliding black holes. That's where missions like LISA come in. The Laser Interferometer Space Antenna, set to launch in the 2030s, will float 3 spacecraft millions of kilometers apart, forming a gravitational wave detector the size of Earth's orbit. While ground-based observatories like LIGO catch the high-frequency chirps of merging black holes, LISA's sensitivity to low-frequency waves makes it the perfect instrument to hunt for cosmic strings. A passing string might create a burst of waves lasting years, a slow-motion siren call from the dawn of time. But why look for them at all? Because cosmic strings could be the universe's ultimate time capsules. Their existence would confirm theories about how fundamental forces separated in the early cosmos, like a fossil record etched into space-time. Some models even suggest these strings could explain strange patterns in the cosmic microwave background, ancient light that carries imprints of the universe's infancy. Others propose that if 2 strings crossed, they might form closed loops that evaporate in bursts of high-energy radiation, leaving behind signatures in gamma-ray telescopes. The hunt is more than theoretical. In 2014, astronomers spotted a peculiar pattern in distant quasars that some argued could be the lensing effect of a cosmic string. Though later analysis cast doubt, the tantalizing possibility remains. Whether LISA finds them or not, the search forces us to confront a humbling truth. The universe might be threaded with invisible scars, silent witnesses to forces so vast and ancient they make the lifespan of stars seem like the blink of an eye. And in their whispers, we might finally hear the echoes of creation itself. What if the key to bending space and time isn't some ultra-rare element or black hole energy, but a substance that weighs less than nothing? Negative mass sounds like science fiction, but it's rooted in real equations, including those behind Miguel Alcubierre's infamous warp drive. Picture a spacecraft sitting inside a bubble of distorted space-time, where the fabric of reality contracts in front of it and expands behind it. No breaking the speed of light, just cheating the system by moving space itself. To make this work, Alcubierre's math demands something bizarre: exotic matter with negative mass, a material that doesn't just weigh nothing, but actively repels gravity instead of attracting it. Here's where it gets wild. Negative mass wouldn't behave like ordinary matter. Drop a ball of it, and instead of falling to the ground, it might accelerate upward, defying gravity's pull. Push it, and it could move toward you instead of away, like a phantom with inverted physics. This isn't just theoretical whimsy. Some cosmologists speculate that dark energy, the mysterious force accelerating the universe's expansion, might be linked to a pervasive, dark fluid with negative gravitational properties. Imagine the cosmos as a balloon being inflated not by outward pressure, but by an internal repulsion woven into the vacuum of space itself. the search for such exotic matter isn't confined to chalkboards. Laboratory experiments with ultra-cold quantum gases have created conditions where particles effectively exhibit negative mass, albeit in highly controlled settings. Meanwhile, observations of galaxy clusters hint at peculiar gravitational anomalies that could, if you squint, align with pockets of negative mass warping space in ways normal matter can't. But the ultimate test might come from studying the universe's expansion itself. If dark energy behaves like a fluid with negative mass, it could explain why cosmic acceleration isn't just persisting but intensifying over time. The catch: negative mass raises thorny questions about energy conservation and causality. Would a warp bubble's creation require infinite energy? Could it trigger time paradoxes? For now, these puzzles remain unanswered, but the mere possibility reshapes how we think about the universe's scaffolding and our place within it. Whether negative mass remains a mathematical curiosity or becomes the cornerstone of a new physics, it forces us to confront a humbling truth. The universe's rulebook might have chapters we haven't even glimpsed yet. And somewhere in those pages could lie the secret to traversing the stars, not by fighting gravity, but by bending it to our will. What if everything you see around you, the stars, the planets, even your own hands, is nothing more than an illusion? A three-dimensional projection of information written on a two-dimensional surface at the edge of the universe. This isn't the plot of a sci-fi movie. It's the holographic principle, a radical idea born from the fiery debates over black holes and information that could rewrite our understanding of reality itself. The story starts with black holes and a simple question: what happens to the information of an object when it gets sucked past the event horizon? Quantum mechanics insists information can't be destroyed, but black holes seem to violate that rule until physicist Gerard T. Hooft proposed something astonishing. The information isn't lost, it's smeared across the black hole's surface, encoded in tiny Planck-sized pixels like a cosmic hard drive. That means everything falling into the black hole, every atom, every photon, leaves a two-dimensional fingerprint on its horizon. Stretch this idea to the entire universe, and you get the holographic principle. Our three-dimensional cosmos might just be a projection of data written on some distant, unimaginable boundary. But how could this possibly work? Enter the AD/CFT correspondence, a mathematical breakthrough that ties string theory's higher dimensional worlds to quantum field theories living on their boundaries. Picture a can of soup, the soup inside, the bulk, represents our familiar universe with gravity, stars, and galaxies. The label on the can, the boundary, holds a quantum theory without gravity at all. The mind-bending part: these two seemingly unrelated descriptions are mathematically equivalent. The equations governing particles on the label perfectly mirror the physics inside the can. It's as if someone handed you a sheet of music and said, "This isn't just notes on paper, it is the symphony." The implications are staggering. If the holographic principle holds, it means every event in our universe, every supernova, every thought in your brain, could be mirrored by interactions on that two-dimensional surface. Gravity, the force that shapes galaxies, might not even be fundamental, just an emergent effect of quantum entanglement on the boundary. Even time could be an illusion, a byproduct of how information flows between layers of reality. Experiments are already testing these ideas. Fermilab's holometer hunts for telltale quantum fuzziness in space-time, evidence that at tiny scales, reality might pixelate like a hologram. Meanwhile, physicists are using AD/CFT to tackle problems in nuclear physics and superconductivity, proving that even if the principle sounds outlandish, its mathematical power is undeniable. So the next time you look up at the night sky, consider this: those stars might not just be distant suns. They could be echoes, flickering projections of something far stranger, written in the universe's hidden code. And if we're living in a hologram, the real question isn't, what are we made of? It's who or what is holding the projector. What if everything we think we know about gravity is wrong? For decades, dark matter has been the go-to explanation for the way galaxies spin faster than they should, stars on the outer edges orbiting as if gripped by invisible hands. But what if the answer isn't an unseen substance at all? What if we've just been missing a crucial tweak to the laws of gravity itself? That's the bold claim of modified Newtonian dynamics, or MND, a theory that dares to rewrite Newton's centuries-old equations to explain the cosmos without invoking dark matter's shadowy presence. At the heart of MND lies a simple yet radical idea. Gravity doesn't behave the same way everywhere. In the weak gravitational fields at the edges of galaxies, where accelerations are incredibly faint, the force might follow different rules. Picture driving a car that suddenly changes gears when you slow down, except here, the car is gravity itself, shifting its behavior when accelerations dip below a critical threshold. This tiny adjustment, proponents argue, perfectly predicts the rotation curves of spiral galaxies without needing a single particle of dark matter. It's as if we've spent decades searching for a missing actor in a play, only to realize the script was miscounted all along. The evidence is startlingly precise. Take galaxy after galaxy, plot the speed of stars against their distance from the center, and MND predictions align almost flawlessly with observations. No halos of invisible matter required. In some cases, like the ultra-diffuse galaxy NGC 1052, where dark matter models struggle to explain its motion, MND sails through unscathed. It's a tantalizing hint that maybe, just maybe, we've overcomplicated the universe, but MND isn't without its critics. When confronted with the titanic collisions of galaxy clusters, like the famous bullet cluster, the theory stumbles. Here, the visible matter and the gravitational lensing effects, thought to map dark matter, are wrenched apart, leaving MND scrambling for explanations. Some versions of the theory invoke phantom dark matter, a mathematical trick that mimics dark matter's effects without the particles, but to many, this feels like cheating. If you're going to reject dark matter, why borrow its shadow? The debate rages on. Supporters argue that MND elegance and predictive power in galaxies outweigh its cluster-scale struggles, while skeptics point to the overwhelming evidence for dark matter's role in cosmic structure formation. Meanwhile, experiments like LISA and future galaxy surveys could tip the scales, either by uncovering dark matter's true nature or revealing new gravitational anomalies MND can't ignore. One thing's certain, MND forces us to question our assumptions. Whether it's right or wrong, it's a reminder that even the most fundamental laws like gravity might still have secrets waiting to be uncovered. And in that uncertainty lies the thrill of discovery. Forget the image of black holes as monstrous giants lurking in galactic centers. What if the cosmos is teeming with their ancient, diminutive cousins, so small they could slip through your hand unnoticed? Primordial black holes, hypothetical relics forged in the chaos of the Big Bang, could be hiding in plain sight, solving one of the universe's greatest mysteries, the missing dark matter. These aren't the black holes we know from star deaths. They're thought to be as light as a paperclip or as massive as a planet, born from random fluctuations when the universe was less than a second old. The beauty of this idea lies in its simplicity. No exotic particles, no hidden dimensions, just densely packed knots of spacetime left over from creation itself. If they exist in vast numbers, these ancient gravity wells could explain why galaxies rotate too fast, why light bends around invisible mass, even why LIGO keeps detecting surprisingly heavy black hole mergers. Imagine two primordial black holes wandering the cosmos for billions of years, finally spiraling into one another. Their collision would send gravitational waves rippling across the universe, a signature just as detectable as mergers between stellar giants. Microlensing surveys are hunting for proof. When a primordial black hole drifts between us and a distant star, its gravity should briefly magnify the star's light like a cosmic magnifying glass. Projects like Ogle and Subaru's Hyper Subprime CAM have scanned millions of stars, catching flickers that could betray these shadowy wanderers. Some tantalizing signals have emerged, short, unexplained brightenings that don't quite match known objects, but the smoking gun remains elusive. Yet challenges loom. Too many small primordial black holes would have evaporated by now, thanks to Hawking radiation, while larger ones would disrupt star clusters we observe to be pristine. And then there's the question of formation. Did the early universe really have the right conditions to birth them in the required numbers? The debate is fierce, but the stakes are cosmic. If even a fraction of dark matter turns out to be these time-worn relics, it would mean we're surrounded by fragments of the Big Bang itself, silent witnesses to the universe's first breath. As detectors grow more sensitive and simulations probe exotic formation mechanisms, one thing's certain: the hunt for primordial black holes isn't just about dark matter. It's a window into the universe's most violent moments, a chance to touch the untouchable and map the invisible scaffolding holding reality together. Whether they're out there or not, the search forces us to rethink the very nature of matter, time, and the hidden architects of the cosmos. The standard model of particle physics has been wildly successful, predicting everything from the Higgs boson to quantum quirks with astonishing precision. Yet it's also glaringly incomplete, like a puzzle missing half its pieces. Enter supersymmetry, one of the most elegant theories ever proposed to fill those gaps. It suggests every known particle has a hidden twin, a superpartner lurking just beyond our current reach. Electrons would have selectrons, quarks would have squarks, and even the photon would be paired with a photino. These so-called sparticles aren't just faint echoes of their counterparts. They could solve some of physics' biggest mysteries, from dark matter's identity to why the Higgs boson is so inexplicably light. The math behind supersymmetry is seductively beautiful. It balances the standard model's equations like a cosmic accountant, smoothing out infinities and restoring symmetries broken by our current understanding. The theory predicts these superpartners should have been spotted by now, especially at the Large Hadron Collider, where protons collide at nearly the speed of light. Yet despite years of searching, not a single sparticle has turned up. It's as if we've thrown the universe's most powerful net into the quantum ocean and come up empty. This doesn't mean supersymmetry is dead, far from it. Some theorists argue we've been looking in the wrong places. Split Sussy, for example, proposes that while most superpartners are too heavy for current detectors to spot, a few, like the neutralino, could still be hiding in plain sight. This hypothetical particle is a perfect dark matter candidate, stable, electrically neutral, and just massive enough to explain galactic rotations without being so hefty it would have already shown up in experiments. Others suggest supersymmetry might be broken in unexpected ways, with sparticles appearing at energies far higher than we've probed so far. It's like searching for a radio station but realizing you've been dialing the wrong frequency band. Future colliders, like the proposed 100-kilometer Future Circular Collider, could finally tune into the right channel, uncovering particles the LHC couldn't touch. The stakes couldn't be higher. If supersymmetry is real, it wouldn't just complete the standard model, it would open a door to a hidden layer of reality, a shadow universe of particles waiting to rewrite physics. And if it's not, well, that might be even more exciting, forcing us to tear up the textbook and dream up something even stranger. After all, the universe has never been shy about surprising us. What if our familiar three-dimensional world is just the surface of something far deeper, like ants crawling across a sheet of paper, utterly unaware of the vast space above and below them? The idea that our universe might harbor hidden extra dimensions isn't just sci-fi speculation. It's a serious theoretical framework that could solve one of physics' greatest puzzles: why gravity is so bafflingly weak compared to the other fundamental forces. Picture this: the electromagnetic force can pin a magnet to your fridge with ease, while gravity, the force that holds galaxies together, can't even keep you from jumping off the ground. The discrepancy is staggering. Gravity is a trillion times weaker than it should be. But what if that's not because gravity is inherently feeble, but because it's leaking into dimensions we can't see? This wild possibility emerges from string theory, which proposes that the universe operates in 10 or 11 dimensions, not just the 3 of space and 1 of time we experience. The extra dimensions are thought to be curled up into intricate, infinitesimally small shapes called Calabi-Yau manifolds, structures so complex they resemble multidimensional origami folded at scales a billion times smaller than an atom. If gravity's force were spread across these hidden dimensions, diluted like perfume evaporating into a vast, invisible room, it would explain why it feels so weak in our 4-dimensional slice of reality. Meanwhile, the other forces confined to our familiar dimensions would remain relatively strong. But how do we test something so abstract? Enter experiments like those at the University of Washington's Earth-Wash Lab, where scientists use exquisitely sensitive torsion balances to measure gravity's strength at microscopic distances. If extra dimensions exist, gravity should deviate from Newton's inverse square law at scales smaller than the compactification size, the point where the hidden dimensions begin to uncurl. Think of it like trying to pour water down a hose. If the hose has a hidden leak, the extra dimensions, you'd notice the flow weakening at a certain point. So far, no deviation has been found, but the hunt continues with ever more precise instruments. Even wilder are the implications for unifying physics. If gravity's true strength is masked by hidden dimensions, it could finally bridge the chasm between quantum mechanics and general relativity. Some models suggest that at extremely high energies, like those moments after the Big Bang, these extra dimensions unfurl, allowing all forces to merge into a single, elegant symmetry. It's as if the universe's rulebook has been written in invisible ink, revealing its full glory only under the right conditions. Could black holes provide another clue? Hypothetical micro-black holes, which might form if extra dimensions exist, could be produced in particle colliders like the LHC. These tiny, fleeting gravity wells would evaporate instantly, but their telltale energy signatures could betray the presence of dimensions beyond our perception. So far, no luck, but the search is far from over. Whether extra dimensions are real or not, their mere possibility reshapes how we see reality. The cosmos might be a labyrinth of unseen folds and twists, its deepest truths hidden not in distant galaxies, but in the spaces between the smallest particles. And if we ever uncover them, it won't just rewrite physics, it'll redefine what it means to exist in this vast, mysterious universe. At the smallest scales imaginable, far beneath the realm of atoms or even quarks, the smooth fabric of spacetime we take for granted dissolves into a seething chaos known as quantum foam. Picture an ocean during a storm. What seemed calm from a distance now churns with violent, unpredictable froth. Now shrink that image down to scales a billion times smaller than an atom, where spacetime itself becomes a turbulent dance of fleeting wormholes, virtual black holes, and bubbles of distorted geometry. This isn't just theoretical poetry, it's a prediction of quantum mechanics and general relativity colliding at the Planck length, roughly 1/10,000,000th of a trillionth of a centimeter. Here, the very concepts of here and now lose meaning, flickering in and out of existence like static on a cosmic radio. This frenzy isn't random noise, it's spacetime's fundamental structure revealing its granular nature. Loop quantum gravity, one of the leading theories attempting to unify quantum mechanics with gravity, suggests spacetime isn't continuous but woven from tiny, indivisible atoms of geometry. Think of the universe as a tapestry where what appears smooth from afar is actually a mosaic of interlocking threads. These space-time quanta, some as small as the Planck length, could resolve one of physics' most vexing paradoxes, the infinite density at the heart of black holes. Instead of a singularity where physics breaks down, loop quantum gravity proposes a rebound effect, a cosmic trampoline where collapsing matter reaches a maximum density before bouncing back outward. It's as if black holes aren't bottomless pits but rather quantum pressure cookers, where spacetime's granularity prevents true infinities from forming. Evidence for this frothy reality might be hiding in the light from distant quasars. Some models predict that high-energy photons traversing billions of light-years should interact with quantum foam's turbulence, arriving at Earth with subtle wavelength distortions, like a marathon runner navigating an obstacle course. The Fermi Gamma Ray Space Telescope has scoured the cosmos for these telltale signatures, though the results remain tantalizingly ambiguous. Meanwhile, tabletop experiments using superconducting circuits are simulating spacetime's quantum behavior, offering glimpses into how geometry might emerge from discrete building blocks. The implications stretch beyond black holes. If spacetime is truly granular, it could rewrite our understanding of the Big Bang, replacing the singularity with a quantum bounce, a moment where the universe didn't emerge from nothingness but rebounded from a prior contraction. It might even hint at a deeper truth, that space and time aren't the stage upon which the universe unfolds, but actors in the drama themselves, emerging from relationships between quantum events. So the next time you glance at the night sky, remember the vast, seemingly serene cosmos is built atop a hidden storm, a quantum sea where reality itself is stitched together one tiny, turbulent thread at a time. Imagine if the dark universe, the invisible stuff making up most of the cosmos, had its own version of light, a ghostly glow we've never seen because it doesn't interact with our kind of matter. That's the tantalizing idea behind dark photons, hypothetical particles thought to carry a dark electromagnetism, a hidden force binding the shadowy realm of dark matter together. While ordinary photons mediate the electromagnetic force we know, light, radio waves, X-rays, dark photons could be the messengers of a parallel physics, a secret network of interactions humming silently beneath our visible reality. The hunt for these elusive particles is like searching for a whisper in a hurricane. Particle colliders like the Large Hadron Collider are ramping up energies, hoping to spot dark photons blinking into existence during high-speed proton collisions. The logic is simple. If dark photons exist, they could occasionally mix with regular photons, leaving faint but detectable traces in the debris of these subatomic smash-ups. It's as if we're trying to catch a shadow by throwing beams of light at walls, watching for the briefest flicker where something unseen flits through. Meanwhile, deep underground, experiments like HPS at Jefferson Lab and NA64 at CERN take a different approach. Shielded from cosmic interference, they bombard targets with intense electron beams, watching for missing energy, a telltale sign that some of it veered off into the dark sector, carried away by a dark photon. Picture a game of pool where one ball vanishes mid-shot, leaving no trace except the silent gap in momentum. That missing energy could be the first clue to a hidden force shaping the cosmos. The implications are staggering. If dark photons exist, they might not just mediate dark matter interactions. They could also explain baffling anomalies like the muon's magnetic moment discrepancy, where these particles wobble slightly off prediction in magnetic fields. Some theories even suggest dark photons could act as a bridge between our world and dark matter, allowing the two realms to interact just enough to leave subtle fingerprints in galactic structures or cosmic rays. Yet the challenge is immense. Dark photons, if they're real, could be incredibly shy, coupling with ordinary matter 1,000 times weaker than neutrinos. Or they might decay into invisible particles almost instantly, leaving detectors grasping at nothing. Future upgrades, like the planned high-luminosity LHC, will push sensitivity further, probing regimes where these phantoms might finally reveal themselves. Whether dark photons remain an elegant hypothesis or emerge as reality's next great revelation, their pursuit underscores a thrilling truth. The universe might be far richer, far stranger than the forces and particles we've catalogued so far. And in that uncharted territory, the next revolution in physics could be waiting. Deep beneath the serene glow of a neutron star's surface, a disaster is brewing. These cosmic corpses, so dense a teaspoon of their material would weigh 1 billion tons, aren't the flawless spheres they appear to be from afar. Their crusts, a crystalline lattice of atomic nuclei crushed into a rigid shell, are under unimaginable strain, and when they crack, the entire universe feels it. These aren't ordinary quakes. A single fracture on a neutron star unleashes energy equivalent to a magnitude 32 earthquake, sending vibrations so powerful they ripple the fabric of spacetime itself. The aftermath of these starquakes might hold the key to one of astronomy's most baffling mysteries, fast radio bursts or FRB. These millisecond-long blasts of radio waves, detected from galaxies billions of light-years away, pack more energy than the sun emits in weeks. For years, their origins were pure speculation, colliding black holes, dying stars, alien signals. Then, in 2020, the plot thickened. Astronomers watching a magnetar, a highly magnetic neutron star in our own galaxy, caught it spitting out an FRB during a violent crustal rupture. The timing was too perfect to ignore. Suddenly, the connection seemed clear. When a neutron star's crust shatters, the sudden release of pent-up magnetic energy could launch these cosmic lightning bolts across the universe. But the real spectacle happens beneath the surface. As the star's crust fractures, it triggers oscillations in the neutron superfluid beneath, a bizarre state of matter where neutrons flow without friction, like a quantum whirlpool. These vibrations, known as R modes, can persist for minutes, even hours, radiating gravitational waves detectable by observatories like LIGO and Virgo. Picture dropping a pebble into a pond. Only the pond is made of spacetime, and the ripples carry secrets about matter pushed beyond its limits. The stakes go beyond mere curiosity. By studying these quakes, we're glimpsing the behavior of matter at densities impossible to recreate on Earth, conditions where atomic nuclei dissolve into a sea of quarks and gluons, a state theorized to exist in the star's core. Every fracture, every gravitational ripple, is a message in a bottle from nature's most extreme laboratory, and the implications stretch even further. Some theories suggest repeated starquakes could explain why certain neutron stars suddenly slow their rotation, as if something inside them glitched. Others propose these events might forge heavy elements like gold and platinum, scattering them into space through associated eruptions. The more we watch, the clearer it becomes. Neutron stars aren't just dead relics. They're dynamos of violence, their cracks lighting up the cosmos with signals we're only beginning to decode. Right now, beneath your feet and in the air you breathe, there's an invisible scaffold holding reality together, the Higgs field. It's what gives particles their mass, what makes the universe stable, what lets stars burn and planets form. But what if this field isn't as stable as we think? What if it's teetering on the edge of a cosmic cliff, waiting for the slightest nudge to send it crashing into a new state, one where the laws of physics as we know them cease to exist? This isn't just hypothetical. It's called vacuum decay, and it's one of the most unsettling possibilities in all of physics. Imagine the universe as a valley, with the Higgs field sitting in a shallow depression, a false vacuum. It's stable for now, but there might be a deeper valley somewhere, a true vacuum with entirely different rules. If a tiny patch of space somewhere in the cosmos quantum tunnels into that lower state, it could trigger a bubble of true vacuum expanding at the speed of light. Inside that bubble, the Higgs field would reconfigure itself, rewriting the very fabric of reality. Atoms might not hold together. Forces could behave differently. Everything we know, galaxies, planets, life itself, would unravel in an instant. The terrifying part, we wouldn't see it coming. a bubble could already be expanding toward us from some distant corner of the universe, and by the time it reached Earth, our last moment would be a silent, instantaneous rewrite of existence. No explosion, no warning, just physics itself turning inside out. This isn't science fiction. Calculations based on the Higgs boson's mass suggest our vacuum might indeed be metastable, stable enough to last billions of years, but not forever. Experiments at CERN are probing this very question, measuring the Higgs properties with unprecedented precision to determine whether we're sitting on a time bomb or a solid foundation. Some theories even suggest that high-energy particle collisions could, in principle, create a tiny bubble of true vacuum. Though the odds are so astronomically low, it's far less likely than winning every lottery in history simultaneously. Yet the implications are profound. If vacuum decay is possible, it paints a picture of a universe where the ground beneath our feet is fundamentally fragile, where the constants we depend on might just be temporary. It's a humbling reminder that the forces shaping our reality are not just invisible, they're unpredictable. And in the grand scheme of things, we're just borrowing time in a cosmos that could rewrite itself at any moment. Gravity holds planets in orbit and pins us to the ground, yet at the quantum level, it refuses to play by the same rules as the other fundamental forces. Electromagnetism has photons, the strong force has gluons, but gravity's hypothetical carrier particle, the graviton, remains frustratingly absent from the particle zoo. The problem isn't just that we haven't found it. Gravitons, if they exist, would be so weak, detecting one would be like listening for a single raindrop in a hurricane. The math paints a stark picture. A graviton detector would need to be so sensitive it could pick up a feather landing on the moon, and even then, it would take longer than the age of the universe to register a signal. This elusiveness isn't accidental. Gravity's weakness compared to other forces suggests gravitons interact with matter a trillion times more feebly than photons do. Imagine trying to catch a ghost with a net made of mist. That's the scale of the challenge. Yet string theory, our most ambitious framework for unifying physics, depends on gravitons existing. In this model, gravitons aren't just particles, they're tiny, vibrating loops of energy woven into the fabric of higher dimensions we can't perceive. Picture a guitar string playing a note so quiet, it's drowned out by the cosmic background hum, except the guitar is the universe itself, and the note is gravity's quantum whisper. The plot thickens when you consider where these gravitons might hide. String theory posits that while electromagnetism and nuclear forces are confined to our familiar four-dimensional spacetime, gravity could leak into extra curled-up dimensions, diluting its strength. It's like water seeping through cracks in a pipe. What seems weak in our world might be robust in others. This could explain why gravity feels so feeble here while remaining central to cosmic structure. Experiments at CERN Large Hadron Collider have hunted for signs of these hidden dimensions by searching for missing energy in particle collisions, potential evidence of gravitons slipping into unseen realms, but so far the data remains silent. Yet the stakes couldn't be higher. If gravitons are real, they'd bridge the chasm between quantum mechanics and general relativity, revealing how spacetime's curvature emerges from particle interactions. Some theories even suggest gravitons could be composites of more fundamental entities, like twists in the universe's quantum foam. Others argue they might leave faint imprints in the gravitational waves from colliding black holes, detectable by future observatories like LISA. For now, these ideas hover at the edge of testability, a reminder that the universe's deepest secrets often lurk just beyond our reach, waiting for the next leap in imagination and engineering. The hunt continues, not just in accelerators but in the cosmos. If gravitons have even a tiny mass, their waves could subtly alter the light from distant quasars over billions of years, a signature telescopes might one day spot. Until then, they remain both a theoretical necessity and a ghost in the machine, whispering from the edges of physics' known frontier. Whether they're ever caught or not, gravitons embody a profound truth. Sometimes the most fundamental pieces of reality are the hardest to see. While we marvel at the cosmic microwave background, the afterglow of the Big Bang stretching back to 380,000 years after creation, there's an even older whisper hidden in the universe's dark corners. Billions of years before photons began their journey across space, an invisible ocean of neutrinos flooded the cosmos, released just 1 second after the birth of everything. These ghostly particles, now drifting through the void at temperatures colder than deep space, form the cosmic neutrino background, a relic so faint, catching even a single one would be like listening for the flap of a butterfly's wings in a hurricane. The challenge isn't just their elusiveness. Unlike the CMB's photons, which we can detect with radio telescopes, these primordial neutrinos have cooled to a frigid 1.95 Kelvin, barely above absolute zero, and their energy is so low they slip through entire planets without a trace. Yet buried in their subtle signals could be secrets about the universe's earliest moments. How matter triumphed over antimatter, why neutrinos have mass at all, even clues about dark matter's origins. That's where experiments like Ptolemy come in, a high-stakes quest to build the universe's most sensitive neutrino telescope, not in space but in an underground lab in Princeton. Picture a detector so precise it can spot the faint recoil of a nucleus when a relic neutrino bumps into it. Ptolemy approach hinges on tritium, a rare isotope of hydrogen, chilled to near absolute zero and spread over a surface the size of a postage stamp. When a neutrino interacts, it should leave behind a tiny burst of energy, a signature so minuscule. The experiment must shield against vibrations from passing trucks, cosmic rays, even the warmth of a researcher's breath. It's like trying to hear a pin drop in a sandstorm while wearing noise-canceling headphones tuned to a frequency no one's ever recorded. The stakes, if successful, Ptolemy could open a window into the universe's first second, a time when quarks were still condensing into protons and neutrons, and the four fundamental forces were barely distinguishable. Some theories suggest these neutrinos might bear scars from primordial phase transitions, cosmic earthquakes that shaped the fabric of reality. Others speculate they could reveal interactions with dark matter particles, offering a backdoor into that shadowy realm. But time is running out. As the universe expands, these relic neutrinos grow colder and more diffuse, their signals fading into the quantum noise. Capturing them isn't just a technical triumph, it's a race against entropy itself, a chance to touch the afterglow of creation before it vanishes into the dark. There's a hidden engine at the heart of every spinning black hole, twisting the fabric of reality itself into a vortex. Picture a whirlpool in space-time, so powerful that even light can't resist its pull. This is frame dragging, the mesmerizing effect of a rotating singularity warping the universe around it. The faster the black hole spins, the more it yanks the very grid of space and time along for the ride, like a celestial spoon stirring the cosmos into a frenzy. And this isn't just theoretical spectacle, it's the violent force behind some of the universe's most energetic phenomena, from supersonic jets stretching thousands of light years to the blinding flares of quasars outshining entire galaxies. Take M87, the supermassive black hole famously imaged by the Event Horizon Telescope. The eerie glow of its accretion disk isn't symmetrical, it's brighter on one side, a telltale sign of relativistic beaming caused by the black hole's dizzying spin. As matter spirals in at near light speed, particles are whipped into jets shooting straight out of the poles, energized by the black hole's rotational fury. These jets aren't just cosmic fireworks, they're the universe's most efficient particle accelerators, capable of hurling material across millions of light years, shaping the growth of galaxies and seeding the cosmos with heavy elements. But how does a black hole, an object so dense even light can't escape, generate such colossal power? The secret lies in the ergosphere, a region just outside the event horizon where frame dragging becomes irresistible. Here, space-time is dragged so forcefully that nothing can stand still. Even if you fired your rockets at full thrust, you'd still be swept along like a leaf in a hurricane. Matter caught in this cosmic waltz gets shredded into plasma, its energy amplified by the black holes spin like a gravitational slingshot. Some particles escape as jets, while others vanish past the horizon, feeding the singularity's hunger. The stakes for understanding black hole spin go beyond mere curiosity. Spin rates could reveal how these monsters grew, whether through steady accretion or violent mergers. A black hole spinning near the theoretical limit might be a fossil from a cataclysmic collision, its rotation a snapshot of primordial chaos. Others, like the quiet giant at our galaxy's center, spin more slowly, hinting at a tamer history. Future observations by next-gen telescopes promise even sharper views of these spin signatures, peeling back layers of mystery surrounding the universe's most enigmatic dynamos. What we're witnessing isn't just destruction, it's creation. The same forces that tear stars apart also forge the building blocks of new worlds, proving once again that in the darkest corners of the cosmos, the most violent phenomena are often the architects of life itself. At the very edge of a black hole's event horizon, where gravity twists space and time into knots, lies one of physics' greatest paradoxes, the singularity. According to Einstein's equations, a collapsing star's core should crush itself into an infinitely dense point, a place where the laws of physics break down completely. But infinity isn't just unlikely, it's a red flag that our theories are missing something profound. That's where Planck stars come in, a radical idea born from loop quantum gravity that dares to rewrite the black hole's fate. Instead of vanishing into a mathematical nightmare, these quantum rebounds could transform dying black holes into the universe's most exotic objects, celestial phoenixes rising from the ashes of gravitational collapse. Picture a black hole not as a bottomless pit, but as a cosmic rubber band. As matter falls inward, compressing beyond the Planck length, the smallest possible unit of space quantum gravity's repulsive force kicks in, halting the collapse and triggering a bounce. The result, a Planck star, a blisteringly hot, ultra-dense object momentarily suspended in a state of quantum defiance. Unlike the black hole it replaces, a Planck star has no singularity. Its core is a seething ball of spacetime foam, where the fabric of reality churns with granular uncertainty. For a fleeting cosmic instant, it glows with the heat of a newborn universe before dissipating into Hawking radiation. The twist, because of time dilation near the event horizon, this entire life cycle, from collapse to rebirth to evaporation, would appear frozen from an outsider's perspective, stretched across billions of years. The beauty of this idea lies in its observational fingerprints. If Planck stars exist, the final moments of an evaporating black hole could unleash a gamma-ray burst unlike any other, a last gasp of energy from the rebounding core. Telescopes like Fermi LT scan the skies for such signals, hunting for anomalies in the cosmic background that betray these quantum fireworks. Even more tantalizing are the gravitational waves. When a Planck star forms, its sudden bounce should send ripples through spacetime, potentially detectable by future observatories like the Einstein telescope. These waves wouldn't match the smooth chirp of colliding black holes, but might instead carry jagged, high-frequency echoes, a quantum ringing in the fabric of reality. Critics argue that Planck stars remain speculative, their physics untested beyond thought experiments. Yet their implications are irresistible. They offer a way to preserve information in black hole evaporation, sidestepping Hawking's paradox. They hint that the universe might recycle itself through quantum resets, avoiding the dead end of singularities. And they suggest that deep in the hearts of black holes, the universe still obeys rules, just rules we're only beginning to glimpse. Whether Planck stars are real or not, their mere possibility reminds us that even in the darkest corners of the cosmos, nature abhors infinite collapse. There's always a rebound, a twist, a hidden layer waiting to surprise us. What if space and time aren't the unchanging stage of the universe, but something far stranger, a tapestry woven from threads of quantum entanglement? This radical idea, known as emergent spacetime, turns reality inside out, suggesting that the dimensions we take for granted might be nothing more than a shadow cast by deeper, invisible connections between particles. Think of it like watching a movie. The smooth motion on screen emerges from countless individual frames, none of which contain movement on their own. In the same way, spacetime could be an illusion, a side effect of quantum information exchanging whispers across the void. The clues lie in the math. Take tensor networks, complex webs of equations that describe how quantum systems store and process information. When physicists model entanglement using these frameworks, something astonishing happens. The connections between particles naturally give rise to geometry, with distance and curvature emerging from the strength of quantum links. It's as if you started knitting a sweater and realized the stitches were secretly building a map of the cosmos. The AD-S/CFT duality takes this further, proposing a holographic universe where a lower dimensional boundary without gravity, like the surface of a bubble, perfectly encodes the physics of a higher dimensional world with gravity, the bubble's interior. In this picture, spacetime isn't fundamental, it's a translation of quantum data from another dimension. But how do we test something so abstract? Experiments with quantum computers offer a tantalizing hint. By simulating entangled qubits, researchers have watched geometry emerge from pure information, like watching a 3D image crystallize from a flat QR code. Meanwhile, astrophysicists scour the cosmic microwave background for anomalies, subtle statistical fingerprints that might betray spacetime's pixelated origins. If the universe is truly a network of quantum connections, there should be limits to how smoothly it can curve, a graininess visible only at the smallest scales. The implications are staggering. If spacetime is emergent, it could explain why gravity stubbornly resists unification with quantum mechanics, because gravity isn't a force at all, but a collective effect, like the way traffic jams emerge from individual cars. Black holes become knots in the quantum web, their event horizons marking where entanglement reaches its limit. Even the Big Bang might rewrite itself, not as an explosion in space and time, but as a phase transition in an information field we've yet to fully comprehend. This isn't just philosophy. If spacetime is a secondary phenomenon, it means the universe has layers we've barely scratched, a hidden architecture where the real work happens in dimensions beyond perception. The next time you glance at the stars, consider this. The vast distances between them, the fabric stretching those points apart, might be the universe's most convincing mirage. And somewhere beneath it all, the quantum threads hum, weaving reality one entanglement at a time. Imagine waking up one day, certain of your memories, your thoughts, even the world around you, only to realize none of it exists. You're not a human being on Earth, but a fleeting fluctuation in the void, a momentary spark of awareness conjured from pure chaos. This isn't the plot of a dystopian novel. It's the bizarre paradox of Boltzmann brains, a cosmic thought experiment that turns our understanding of reality inside out. The idea springs from thermodynamics, specifically Ludwig Boltzmann's work on entropy, the universe's tendency toward disorder. Given enough time, even in a state of maximum entropy, random fluctuations could theoretically create order out of chaos. Most fluctuations would be tiny, a brief alignment of atoms, a fleeting ripple in the cosmic background. But in an infinite universe, the improbable becomes inevitable. Given trillions upon trillions of years, there's a non-zero chance that atoms could randomly assemble into a fully functioning brain, complete with false memories and a hallucinated reality. And statistically, in a vast, eternal cosmos, these disembodied minds might outnumber real, biologically evolved beings like us by an unimaginable margin. Here's where it gets unsettling. If Boltzmann brains are more likely than ordinary observers, how do we know we're not one of them? The coffee in your hand, the screen in front of you, even the sensation of reading these words, could it all be a temporary glitch in the fabric of nothingness? Cosmologists recoil at this idea, not just because it's existentially jarring, but because it undermines the very foundation of scientific inference. If most conscious experiences are illusions, how can we trust any observation about the universe? This paradox forces us to confront profound questions about the arrow of time. Why do we remember the past but not the future? Why does entropy always increase? The traditional answer points to the low entropy state of the early universe. The Big Bang set the clock ticking. But if Boltzmann fluctuations can spawn self-aware entities, then time's arrow might not be so absolute. In an eternal, oscillating cosmos, brains could pop into existence, remembering a past that never happened, their perceived flow of time just an accident of their momentary configuration. Critics argue this scenario is absurd, not just philosophically but mathematically. The probability of a fully formed brain fluctuating into existence is so vanishingly small, even cosmic timescales might not suffice. Others counter that certain cosmological models, like eternal inflation or cyclic universes, could provide the endless time and space needed for these statistical anomalies to dominate. The debate rages on, with some physicists proposing the Boltzmann brain problem as a litmus test for theories of the universe. If your model predicts more disembodied minds than real ones, it might be time to go back to the drawing board. Ultimately, the Boltzmann brain conundrum isn't just about hypothetical fluctuations, it's a mirror held up to our deepest assumptions about reality, observation, and the nature of existence itself. Whether a fleeting illusion or a genuine revelation, it reminds us that the universe's greatest mysteries aren't just out there in the stars, they're woven into the very fabric of consciousness, waiting to unravel our certainty one thought at a time. From ghostly dark matter weaving the cosmos together to the quantum foam frothing beneath reality's surface, these 30 forces reveal a universe far stranger than we ever imagined. Yet here's the humbling truth: everything we've discovered, from black holes to cosmic strings, accounts for barely 5% of existence. The rest, a vast, uncharted wilderness of dark energy, unseen particles, and forces we've yet to name. Think of it like exploring Earth while only knowing the outline of a single continent. We've mapped the visible stars, the familiar atoms, the equations we can test, but the real story lies in the shadows. What if dark matter isn't one thing but an entire hidden sector of particles, each with its own rules? What if gravity's weakness isn't a quirk but a clue to dimensions curled tighter than atoms? The forces we've uncovered so far aren't just answers, they're signposts pointing to deeper mysteries. This isn't the end of the journey. The James Webb Space Telescope is peering further back in time than ever, capturing light from galaxies so ancient their stars might be made of primordial physics we've never seen. Underground labs are listening for whispers from dark matter particles that slipped past every detector so far. Even quantum computers, simulating conditions no lab can recreate, might stumble upon forces that rewrite the laws of reality. So stay curious. The greatest discoveries in science didn't come from sticking to the known, they came from asking, what if, and daring to look where no one had before. Whether it's a fluctuation in the cosmic microwave background or an anomaly in a particle collider, the next cosmic force could reveal itself any day. And when it does, our map of the universe, that tiny 5% we thought we understood, will expand once more into the unknown, because the cosmos doesn't owe us answers. It's up to us to keep searching.